Welcome back. I actually want to make one, technical correction to what I was teaching you in the last video, and then I'll introduce you to friction. So this is where we left off in the last video, and I was calling this the normal force. And I really should have called it the component of the gravitational force that is I guess we could say perpendicular, or I guess we could say normal to the surface that the mass is on. And the reason why I'm making this distinction is because this is the pull of gravity, and actually the normal force is the offsetting force, right? In Newton's third law, every action there's an equal and opposite reaction. The normal force is officially the force that this inclined plane is actually exerting on the mass and keeping the mass from falling into the inclined plane. So the normal force is actually by definition this force. That doesn't change how we did that last problem, but I just want to make sure that we have our definitions correct, and you don't go and argue with your teacher that no, this is the normal force, because Sal told me no, I'm sorry, I was always bad with labels, and this is another label, but this shouldn't be the normal force. This could be the force of gravity that is perpendicular, force of GP or something. So I just want to correct that, and now with that out of the way, let's learn a little bit about friction. And hopefully that made a little sense to you. In magnitude, the normal force is equivalent to this force. It just goes in the opposite direction, right? Because you have an equal and opposite force, and that keeps the mass from falling into the inclined plane. So let's clear this and get rid of the inclined plane temporarily so that we can just simplify things and learn a little bit about friction. So everything we've been doing so far involved a mass on a sheet of ice so that we had no friction. But now we'll have a mass on a sheet of dirt. I thought I was using the line tool. Well, that's good. This my attempt to draw a line looks like a surface that has friction on it. Let me put a mass on it now. So instead of ice on ice, we'll have a dirt brick. There's my dirt brick sitting on the ground. And let's say this dirt brick is 10 kilograms. It's a 10 kilogram dirt brick. And let's say that I pull or I push, either way, it doesn't matter. I push in that direction with a force of, 1,000 newtons. So this force is equal to 1,000 newtons. If we had no friction, if this was ice on ice, this would be a really easy problem. You just say F equals ma. So the force is 1,000 newtons in the right direction. Divide that by the mass, and you'd get 100 meters per second squared. So you'd get this really tremendous acceleration. But now we have friction. We have the contact between the brick and the ground, and it's going to make it a little bit harder to push, as you've experienced. When you're pushing something on ice, it's easy, or especially on oil on ice or something like that. And when you push it on the ground or on your carpet, it's much more difficult. So how do we think about friction? So I will introduce you to a concept called the coefficient of friction, and the letter that people normally use for it is this. I think it's called mu, because it's kind of like an M. And this is called the coefficient of friction. Coefficient, does it have two F's? I think it does. Coefficient. It's a good thing I'm not teaching you spelling. Coefficient of friction. And every surface, or especially when you're kind of rating one surface touching another surface, it will have an associated coefficient of friction. And so ice on ice, or ice on oil, or oil on ice might have a very, very low coefficient of friction. And I'll show you how we use this. And if we have sandpaper on sandpaper, that'll have a very, very high coefficient of friction. So this is really just a constant term that tells you how much friction there is between a surface and the object. And this is how we use it. This term tells us that the level of friction is always going to be proportional to the normal force on this object. And that's why I wanted to make that little technical correction. And what's the normal force on this object? Well, we know that the force of gravity is pulling down on this object, right? The force of gravity is pulling down. And what's it pulling down at? Well, the acceleration of gravity, we said, for approximation purposes, is 10 meters per second squared. So 10 meters per second squared times 10 kilograms, it's really 9.8, but 10 times 10, it's 100 newtons, right? So that's the force of gravity. Force of gravity is equal to 100 newtons. And the normal force is essentially the force that this ground exerts upward on the block that keeps the block from falling into the ground. So the normal force has to be equal and opposite to the force of gravity. So the normal force, and I know it's getting a little bit messy, is the exact same magnitude, but it's going in the opposite direction. And it's going to be 100 newtons upward. and the force of friction. And what is the force of friction? The force of friction is essentially always acting against whatever direction you're pushing in or pulling in. So if I'm trying to pull the block in this direction to the right, the force of friction is going to be going to the left. But if I was trying to pull the block to the left, the force of friction is going to the right. And they also call this a shear force. And it's always acting against you. And wind is the same thing. Wind resistance is also a frictional force. So that's the way you should think of it. It's kind of interesting. You would think that at some point it would work for you, but no matter which direction you push in, it's always working against you. And so how do we calculate it? So let's say that I was just told by the people who made this ground and this block that the coefficient of friction of these two materials when they rub against each other is 0.2. So in this example, the coefficient of friction is equal to 0.2. And if you have it on a physics exam, they'll tell you like the coefficient of friction is point something something. So what do we do with that? This tells us that the frictional force, the force of friction or the shear force, is going to be equal to 0.2 times the normal force, or 0.2 times the force of gravity. You can do it both ways. I always think of it as the force of gravity, but you could use either one because they have the same magnitude. So you could say that the force of friction or the shear force is always going to be equal to, you could say the force of gravity or the normal force times the coefficient of friction. And that makes sense because if I had the same surface but I had a much heavier block, then I'll have a lot more friction. That just makes intuitive sense to you. You're able to push something that's pretty light on your carpet, but like a chest of drawers or your bed, it's a lot harder to push on your carpet because it's a lot heavier. And so that's why the force of friction, and we're lucky for us that it's proportional. It could have been, quadratic or something, but it makes the math easier that the force of friction is actually proportional to the weight of the object, we could either say it's proportional to the weight of the object or the force that the floor is exerting upward on the object to keep the object from falling into the floor. So either way, let's just do this problem. So what's the force of friction here? The force of friction in this problem is going to be equal to the normal force or the force of gravity. We could use either one. So that's 100 newtons times our coefficient of friction. They'll always give you that. Sometimes you have to solve backwards for it, but I think you get the point. So the force of friction is going to be equal 0.2 times 100 newtons. The force of friction is going to be equal to 20 newtons. And force is a vector, so what direction is it going to be acting in? Well, it's going to be acting in the opposite direction that I'm trying to push the object. So it's going to be going to the left. So what is the net force on this object? I'm pushing to the right at 1,000 newtons, and then friction is essentially kind of pulling back at 20 newtons. So the net force in this direction, so we could call it the force sub net, which would equal 1,000 newtons. It's going to be in this direction, right? Because 1,000 is much bigger than 20, so it's 1,000 minus 20, which equals 980 newtons to the right. And so if I wanted to figure out how fast is it accelerating, well, to the right, it is accelerating at, force equals ma, so force net is equal to mass times acceleration, so 980 is equal to 10 kilograms times acceleration. So acceleration is equal to 98 meters per second squared in the rightward direction. And that makes sense because my force of friction is relatively small compared to how fast I'm pulling or how hard I'm pulling, and maybe I should have done this with 100 newtons, but I think you get the point. And if there was no friction, the acceleration would have been faster. It would have been slightly faster. It would have been 100 meters per second squared. So hopefully I've given you a little bit of an intuition on what friction is, and I've corrected my labeling mistake on normal force. And I'll see you in the next video where we'll apply our friction skills back to the inclined plane problem. I'll see you soon.